Welcome, everyone. It's Friday. It's the last lecture, I know. Everybody's excited. We are going to talk about caches. If I don't butcher this lecture as well, it's going to be a very fun one, I promise. And we were, just first of all, to remind you, this is reading about this lecture. And I told you, maybe this wakes you up. This is a part of the lecture from which it is very easy to ask a lot of questions in the exam. Okay, so as an examiner, doesn't matter if you want to do an easy exam or an incredibly hard one, this topic is like a gold mine for you trying to come up with questions. You know, I can make an entire exam lasting 6 hours just coming up with questions from these two lectures. And Ono reminded me that I should make sure to have a proper lecture because the students should understand it, because it will end up most probably as 1 or 2 questions in the exam. So public service announcement has been made. Let's continue with our topic. So yesterday we were discussing about memories. In the first lecture we saw how we made memories. We said, okay, there are the flip-flops that we know of. And then we introduced these array-like structures. In this array, it was organized in a 2D structure. We said you can access them efficiently, better than flip-flops. We could put more bits per square area if we were to use these 2-dimensional arrays. And then we differentiated between static RAMs and dynamic RAMs. We said static RAMs are more robust. They are slightly larger, but they are fast. They don't have any problems. Then we came to the DRAM persons, the hippo story. The DRAMs are small. You can put much more bits in the same area when you use the DRAM technology. But you had to sacrifice a lot. The first thing was that these memories are called dynamic because you write to them after a while. The way you write is you put some charge on a capacitor, and this charge doesn't stay there. It slowly evaporates, disintegrates, goes away. The electrons that you say stay here don't remain there forever. And the problem is they lose the charge, and after a while they forget what you have told them. So you had to go and read the entire memory content and write it back all the time. So in most RAMs, you do this every 20, 50, 60 milliseconds, or maybe 200 milliseconds, 5 to 20 times a second. The entire 16 gigabytes of your memory or whatever are completely read out and written back. It's crazy. It's not nice. Then there is the other problem. Because you have a little bit of charge on a capacitor when you are reading it, the moment you read it, you actually destroy the content. So after you have read it, you had to write it back again. We are doing all this thing because we are mostly interested, we are sacrificing all this, or we are keeping up with all these ridiculous demands. It's a memory, you write it, you read it, it forgets. Okay, let's write it back again. You write it, you keep it there, it forgets. You say, okay, you know what? I'm going to put up with the demands of this guy. I'm going to write it, and then what was the value? Here is the value. What was the value? Here is the value, continuously. Why do I do this? Because it's important, or it was important in this case, to have as much memory as possible in the smallest area. So we have competing demands of the memory, and one of them was the size. So people wanted to have large memories. Of course, if you ask anybody, they say, we want the memory to be fast. And then you realize you cannot have both. And because of mainly also because of the issues we will talk about here, people soon realized we can get away with slow memories, but there is nothing substituting size. So there's a lot of technological ideas went into making the memories larger. And we said, we are clever, we will figure it out how to make slow memories appear fast. And this is what we will talk about today. The other thing that we will every now and then also remember is the bandwidth, or how much data we can move back and forth between these memories. So just to keep in mind, these are some of the things that we discussed. And ideally, you want to have infinite size, infinitely fast, infinite bandwidth, et cetera. Problem is we cannot have it. So this is what we ended up with. We said, okay, this is my main memory. It contains, it's the size that I want for my computer. It's made out of DRAM. It's a slow memory, and I can have lots of it. I can have 30, 60, 200 gigabytes of DRAM in my system, and it's okay. The problem, if I want to read something from here, I provide an address, it takes a long time. Now, in the beginning, when you had a CPU, this one was running at the same speed as the main memory. This is like 1970s, maybe beginning of 80s. This was true. At that point, they started making CPUs go ever faster, and then the main memory guys had these two dilemmas. I can either make it large, or I can make it fast, but not both of them. So the idea of caching came out. They said, you know what? If I can put a small memory that when the processor looks at the main memory, he sees this small memory. Because the memory is small, then the memory accesses will also be very fast. And I've solved my problem. CPU accesses this small memory. Every access to here is more or less the same speed, or is tuned to the speed of the CPU. We can do this because if the CPU gets faster, maybe we can reduce the cache so that its speed remains compatible, and I have a nice ecosystem. And then there is a big, slow memory. Who cares? What's the problem here? Let the record show that people are looking in amazement. Yes? You have to decide what you want to store in the cache. Yeah, because there was a reason that we had this memory. We wanted it big. And if we could get away with a small memory, why did we have this? So we, from an application point of view, we have need for storing larger arrays, for working on larger data structures. And this smaller memory is a very small portion of it. And we need to somehow manage that the data that we want, the data that we can operate with, ends up in this memory. Now, we talked about this. We can have automatic methods where there is some hardware, some intelligence sitting in between here that automatically realizes it's a guru, knows it, and decides, aha, in this region there is some data, and I know this user running whatever application here is going to use this data. So let us copy it over while he's doing something else, and the moment he wants it, the data will be there. This would be ideal, and we cannot reach this ideal, perhaps, but we can get very close to it. So there are smart ways of trying to guess what data, what instructions will be needed in the next few cycles. And we talked about that. We said there is this issue about locality, meaning that we have two ideas. One is temporal locality. This means it's in time, that if we access one data structure, one portion of the memory, it is very likely that we will be accessing the same memory again. The bad analogy is, since you are coming to this class this week, next week you will show up again. Nobody's laughing, okay? The second one is the spatial locality, meaning that if we are accessing some data, the neighboring regions will probably also be accessed. Why? Because it's a part of a larger data structure that you're iterating over. Maybe it's a record which has different entries, and you access the ID, then you will access the name, etc., etc. So by taking advantage of these things and nothing supernatural, you can actually have management that moves the data into the cache without you explicitly doing it automatically. Of course, there are systems where you can also do this, manually by programming. You can prefetch data and put it in a memory that is close to the operating units. Anybody programming GPUs? Not yet. Not yet, okay. When you program with GPUs, you have some scratchpad memories that work that way, that they want you to load, bring some data structures that they can operate on in advance. So caches are used, is a generic name. It means a hidden location that allows you to bring data that is going to be used or commonly going to be used closer to where the data is actually going to be needed. So the idea in the computer architecture, because we were having these issues with size and speed, then was decided, because once you realize that you can actually make the memories appear as fast as a small memory, there was no more need to really concentrate to hit a very fine balance between them. The DRAM manufacturers went all size. They said the caches is somehow going to mask the deficiencies in speed, and we are going to do it. It's not like they completely gave up on it, but they concentrated more on the size of the memory, leaving SRAM-based caches to take up the slack. So, caching basics. We know that we can take advantage of this locality, so we need to find methods so that when we are moving data in and out, we have to understand what kind of things we have. The first thing is, in theory, you could store a single word, 32 bits, 8 bits, 64 bits, whatever your size of your processor is, in one cache location. But due to the spatial locality, since if you are accessing one data, you will be needing most probably also the neighboring data. Caches usually work on blocks, or sometimes called lines, which is a number of memory locations side by side. So this could be 8 words of 32 bits, 16 words of 8 bits, or whatever. Then, when you are trying to read from the side of a, let's actually have this here. So just to briefly show, this is the main memory as you see it, as a programmer sees it. There is an address. To this address, there is a corresponding data. It resides in this big memory. If we provide the address, we know where to look. We can fetch this data, return it to this processor that's asking for it. So processor provides the address, you go to the main memory, this is or ignore the thing in between, the address comes here, we look it up, we take it, we bring it back. Okay? So this is the thing that we want to do. In between now, we are putting this cache structure, we are going to talk about what goes on here and what kind of options we have, but basically the thing is, once there is the address, this is the magic cache, and you look at the address comes into the cache and says, do we have this data the guy is looking for? If we have, then we have a hit. And the moment the data we are looking for is already somehow magically stored here, we don't have to, go any further. We can stop looking and return the data. So this is what we call the hit. The miss is, you have the address, you know what data you're looking for, somehow the cache knows that this data is not there. How? We are going to discuss in a few moments. Then it's a miss. It's not in the cache, so we have to go to the next level to look for the data. Now, this thing can also go multiple levels, so it's not like you can have only one level of cache. So you can have a first level cache, you miss it, you go to the second level cache, which is larger, slower, but not as large. Then you can go to level 3, level 4, level 5. Finally, at some point, you are going to arrive at the physical last resting place of the data. So far, so good? Eerily quiet. So, here are some of the issues now. What happens if we have a miss? We don't have it in the cache. We are going and bringing it back. And while we are bringing it to the processor, maybe we could put it in the cache because we use it now. Next time, we are also going to use it. But here is the thing. The cache is not as large as the memory. If I'm putting something here, something has got to go. You can only have so many data in the cache. If you're bringing a new friend and you are only allowed to have 16 friends, whatever, you say, okay, I'm kicking you out. The thing that I like most is like these lists, 100 best pop artists of all time. And you say, okay, what happens when a new artist comes? Who are you going to kick out first? It's the same kind of situation. Okay, so there are some decisions that we have to make so that we can end up making a smart cache that can take advantage of these localities and give us, on average, the best memory access time that we need. Because the problem is, why is this processor asking for data? For example, he wants to load something, and the operation depends on the data that he has loaded. If you make an access, and it takes 1, 2, 3, 4, 5, 6, 7, 8, 9, 2000, 2001 cycles, maybe this guy cannot do anything else until this data arrives. So it doesn't matter if this is a very, very fast processor, if you cannot supply him with enough instructions to tell him what to do, or the data to operate on, it really doesn't matter how fast this can work. He will be waiting for the memory to deliver him data. So from this point of view, it's important to at least have the illusion of having access to a very large and very fast memory. So what kind of problems do we have? Well, these are the questions. So I told you this is like this magical thing. Somewhere here there is the data. And where and how do we place a block into the cache? And how do we find it? And then there was this other issue that we were replacing things. So once we have a miss, we realize the data here is no good. We have to go find nice, fresh data and his friends, and we are bringing them back to the cache. Some of them have to go. What happens now? The other thing is granularity of management. I told you that when we are looking for one data, maybe we want to take advantage of this spatial locality and not only transfer the data, but also its nearest neighbors. So if I'm looking at this one word, maybe I want to copy 4 words or 8 words or 16 words together. Why? I mean, which one is better? Shall I copy 4 words, 16 words, 64 words? What's the block size that gives us the best performance? Write policy. Write policy we are going to talk about, hopefully at the end of the lecture. Imagine that the data that we want to access is in the cache. Now we write to this cache, and the data is in the cache, so we can quickly write it and continue operating on it. But at some point, this is just a copy of the data that was supposed to be in this big and slow memory. If I keep on changing this, at some point, I should also let this poor memory know that, you remember the guy that I copied over from you? It's now completely different. So how are we going to do this? Every time I change, shall I also change this? Or do I have some way of telling the main memory that I am done with operating on this copy that I had? It's now completely brand new, you can have it. The next thing is, and this is a bit nebulous here, I just said address and data. Inside the processor, you realize you have actually 2 streams that is coming. One of them is telling the processor what to do. These are the instructions. And then we have another stream which provides the data for the operations. So do we treat them the same or do we treat them separately? All of the answers to these things are going to decide what we are going to do or how we are going to operate with the memory. Question?
What happens if we load something from memory, we work on it in the cache, and we were trying to write it back? Someone else has tried to, or has kind of reserved this memory space, or has it used for himself, and just overwrites data. Wouldn't that be corrupted data then, or how did that?
So your friend points out another problem with what I just said. So you have a copy of the data here in the memory, and while you are changing this, if someone else, maybe not this processor, maybe another processor is accessing the same data here, not knowing that there is a copy there, wouldn't there be chaos? Yes, there would. And this is a thing called cache coherency. It's one of the biggest discussions these days about how to handle these things. It all started very innocently, if you remember, that the processor wasn't as fast as the memory. Then we will put all kinds of tricks around it, and we invent some new problems that we also have to deal to solve with it. It's fun. We'll come to that. Okay, so this is now the view that we have. It's a bit similar to what I have here. So you provide an address, you come into this cache location, you have somehow a bookkeeping location. We call this a tag store, tag. We will come back to it. And then we have the data store, which actually stores the memory block. So your data is going to be in this part of the cache, and somehow the bookkeeping is being done on this part. Give us a few minutes, we will discuss how this works. And the bookkeeping will tell you, once it sees an address, whether or not this address we are looking for is present in the cache. It can say, hey, I hit. If he hits, then we know where the data is, we can retrieve it. Maybe we can retrieve it immediately, maybe we need a few steps. Otherwise, we say, whoops, it's not in this cache location, go to the next level. And the next level, mind you, could be another cache, which is larger, but maybe a little bit slower. Now, from the point of some poor processor trying to access it, you can see the following thing. So you're looking at the cache hit rate. So you make 1,000 accesses, 900 of them are found in the cache, 100 of them are not found. So you say, I have 90% of a cache hit rate, which also means that you have a 10% miss rate. And what you are actually interested in is, how fast can I actually, once I have an address, what's my average time, statistically speaking, that I can operate? And this is simple. You say, what's the hit rate, and how many cycles does it take to service a request that is hit? And then we say, plus we have some of them are misses, and these misses take longer. If we multiply them, what we are going to get is the average memory access time, or AMAT. And this might give us some idea about how fast we are operating. And notice, you shouldn't get really, you shouldn't take these things as prophecies. So is reducing the average memory access time always beneficial for performance? You could ask yourself this question. Yeah, sorry.
Is there a tag store for like every level of cache separately, or is there just a big one for the whole thing?
Once again, the tag store. The tag store, so the question is there a tag store for the entire cache hierarchy, or is there one individually for each level? You will see they are completely independent. So every level of cache has its own tags. It has its own set of parameters that we were talking about, own set of solutions we were talking about before. So it could be also that the write policies of different levels of caches are different, for example, as well as the tags, as well as any other parameter you have.
So does that mean like we're constantly asking, oh, is my data in this level? No, is it in the next one? Is it?
Yes, but imagine, look at this thing here. You get an address. You don't know what happened before. You don't know if this one was asked. You're kind of happy that someone is asking you out. You're not saying, did you ask someone else? Am I the first one? No, you get the address, say, do you have the data? You say, here it is. Or say, oh, sorry, go to the next one. And then the next one is exactly in the same position, right? There comes an address, a request. I'm looking for this address, and you're not saying, I'm not talking to you. You went to that L1 first, then you asked L2, now you come to me. It's over. No, doesn't work like that. But it's a good question, fair one. Frank should stop with analogies. Yes, okay, I get the point. Especially if I have 81 slides and I'm at number 7. Yeah. Okay, so we will start with a basic cache design, and then we will try to see how we can make it better. Just so that you understand what the basic principle is. And trust me, we already covered a lot. A lot of it is now going to be discussions and details about what we can do. Now, what we can do whenever we are thinking about it, and once we decide that the caches are going to have, are not word size, but they come in blocks, you can then immediately say that I'm going to see the memory as not individual words, but as a collection, as a set of blocks. And these blocks are a couple of memory locations at the same time. And so now you say, okay, I am not looking at individual addresses, but I am looking at blocks of data. Every 16 data word is a block. So it means that I don't need the last 4 bits of the memory address, because I know that everything that falls, you know, all the 16 come as a group. You don't call them out one by one, you take them as a group. So this is the blocking thing. And then you say, okay, so now I only have to care about not the all addresses, but only the size, only the number of blocks that are in the memory. And so here there is a very toy example. I'm sorry for this. So this is an 8-bit address. So the total, you realize, is a kiddie problem, right? The main memory in this case, 8-bit address. How many locations do you have? 256, right? So it's not a memory, you know, it's an example in a book. And then you have 8 bytes in one block. So this was decided that you are going to have 8 bytes in one block. So the last 3 bits are going to tell you, is this the first byte in the block, the second byte, the third, the fourth, the fifth, the sixth, the seventh. We know that data is organized in blocks. So every 8 byte comes as a block. And then we have the index that is going to tell us where I can, in what location of the cache I can find this thing. So the very, very simple thing you can do is, you look at the address, you say, this part is for the block. And then you say, I have a cache that physically has, for example, 4 locations. And you say, whenever the address is, you look at the address, if this address, these 2 bits are 0, 0, it will be in this location in the cache. If it's 0, 1, it will be here. If it's 1, 0 here, 1, 1 here. We call this direct mapped cache. The moment you have the address, there is a portion of the address where you can look into, and you immediately know if this location, your data is in there. And now once the data is in there, the question is, hey, there are many, you can fit, in this case we have 3 bits, so that means 8 locations. I can have multiple data that can map to the exact same location. How do I know which location I'm looking at? I need to keep a tag. Because, let me just write you the 8-bit example. Later on we will talk with the 32-bit ones. Let me hide this for a second. Let's bring this up. So 8-bit address, right? Something like 01000101. Now, according to this thing, we say, this is the byte in the block. This is the 5th byte in 8. This guy tells us the index. Cache location number 0. If you notice, there are actually 4 different sets of data that could be put in the same location. 1000, 1100, 0000. So if I'm storing it, if somewhere I am storing the data that corresponds to this line, and I'm storing actually, I'm actually storing 8 bytes. This is my cache line. So this is byte number 0, number 1, number 2, number 3, number 4, 7. And I'm looking for this guy, the fifth one, in the cache. Notice that I seem to have 8 locations where I could put it. So there are actually 8 bytes. So this is address location 000. This is 001. 10, 011, 1001, 0111, okay? So this is now my cache line. It contains 8 bytes. The byte I'm looking for is byte 5. And I stored, the cache is keeping 8 bytes in location 00. And now I have the tag, and each tag has to tell us so this is again 0001. Yeah. This tag is telling us that I am keeping the memory address, the memory block corresponding to 01 in the cache line 00. If I have another address, let's try another one, okay? Are you ready? I need a random number generator, yes. Tell me. I need 5 more. No, don't make 0, 0. Let's make 1, 1, okay. Sorry, I mean everything but 0, 0. There was a 12% chance. 101. Okay, same thing. This is an 8-bit address. 101, okay. You said 110, I misheard you. So this one says it's the 6th byte. The 6th byte. It is which location in the cache? Where would this guy go into the cache? Yeah? Third one, 011. So 0, well, yeah, 0001, 1011, third one. And the number 6, so we are looking for this guy. This is the one we are looking here. But we also have to notice that this guy corresponds to him. This is a tag. So the address goes 10011 and then 110 because we are looking for the 6th one. So this is how we can resolve. So these are all good. Now let's have a bad one. How about this? We want to access this. So this is still the 6th one. This is the 6th byte. So we are in this column, okay. We know where the cache is. It's 011. So it's again, sorry. 0. This corresponds to this one, sorry. So the previous one, we had the tag 10, but this time the address is different. It's a different memory block. We look at it, 00. We come here. We see that there is something in the cache, but we look at the tag, and the tag says 10. We now realize, okay, I have something that corresponds, in my third row of my cache, but this thing does not have the same tag as what's in there. I don't have it in my cache. Notice that I could have 4 different sets of data that could end up in this cache, but the one that I have from the previous access is not the one that I want now. Although these parts are exactly the same, this data is not the one I'm looking for. So this would be a miss. I would have to flush it and bring the data back from the memory. We'll do it a few more times. There are also examples. Oh, that's silence. Can I? Okay. So, once again, what we do, cache access. So the index goes into the tag. We check the index bits in the address. Do we have something? If we have something, we have the data. So we check whether or not we have the data there. we compare the tag bits in address with the store tag in the tag store. And if they match, if the block is in the cache, we match the address, and then we say, hey, we have this in here. Now, here's a bigger example of the memory divided into these blocks. The problem here, so this is the direct mapped cache. It's very easy to detect, given any address, it's very easy to detect whether or not you have something in the cache or not. Because the moment you have the address, you can directly look at where the things are and directly determine if it's there. And for every cache location, there is a single tag. You are telling that, hey, the data that is stored here has the tag identifier of this. Now, in a real example, not 8-bit, in a real example, actually the tag would be quite large. You know, if you have a 32-bit address, you have 4 cache or 8, 16, 20 cache locations. A few bits would be addressing the index. And now you would have 20-something bits for the tag. It's not like it's a 2-bit story. It's just that the example here chosen was a little bit too small. You also have some bookkeeping locations. You may want to, for example, store whether or not the data you have is valid. There is actually something there. It's not just some random garbage data that's there, but it was actually transferred. It's a valid data, so you may want to do some bookkeeping. And as I said, the one problem with the beauty of the idea is that in a direct mapping, the A block can only go to one location. So if you are looking for data in this entire data store in a direct map cache, given the address, you know that it will be in one fixed location. The address already tells you where it is. It's very practical. There is a small, slight issue with it. So this is the way it works. So you get your address. This is the example that we had. This is byte in the block, so tells which block we are looking for. The index tells in which level, in which line of the store we are. And the tag goes in here, so tells you what it is. And we have here an additional valid bit. Now, once you have this, you can check the index. From the index, you get the tag. You see whether or not this row is valid. You check the tag, compare it against the tag you have. So this is the tag of the address that I am presenting. This is the tag of the data stored in the cache. This tells us that there is actually some data in the cache. If those guys match, then I have a hit, meaning that on the line corresponding to this row here is my data. I pick the data, but the data is not the entire data because I have 8, in this case, I have 8 bytes here. I don't want all 8 bytes. I just want the byte addressed by these 3 bits. So this 8 to 1 multiplexer, so byte in block selector, and then I get my data out. Okay, Ish? Who says, I have no idea what you're talking about? It's not a nice question to ask. Obviously, you will not say, I have no idea. Of course I know what you're talking about, Frank. Let's move with easy stuff. Now, the problem here is, if you happen to have a set of program that ends up going, I don't know, that has a for loop that goes every 8 address or something like that, you may, although your entire cache is available, you may always end up trying to access the same line, which is very, very annoying. You know, you have bought yourself, you are the designer of this processor, you got a 16 kilobyte, very, very fast cache. You paid a lot of money, meaning a silicon area for it. You put it into your system. Now you're running a program, and the program is accessing every 1024th address. You look at the way the mapping goes, and you realize that all memory accesses always want to go to this one location. I have maybe 1,000 locations in my cache, but every data access comes exactly to the same place. I'm saying, this is not fair, it's crazy. I mean, don't do this. 999 places are empty, and every memory access goes to the exact same place in the cache. And then you are saying, you know, this is maybe not the best idea. So this is this 0% hit rate case. Although the cache is large enough, because you don't have any flexibility in where you put the data, you end up having 0% hit rate in that level of cache. You see, this is the issue that we have. So assume the addresses A and B have the same index bits, but the tags are different. So they are not the same address. They correspond to different tags, but the index bits are the same. So if you have a data access like A, B, A, B, A, B, A, B, whatever, no matter what you do, you are never going to get a cache hit. If you are not getting a cache hit, why did you put that cache there in the first place? You know, don't try to do this. We call these things, so this is one of the problems of our caches. So when you are dealing with caches, you have these sets of problems. We call the misses that come because we cannot find a location in the cache for them. We call them conflict misses. It's not like the cache wouldn't have space. The cache has enough space to take up the data. It's just that the way we organize the data, every address only maps to one specific location in the cache. And if you end up always accessing the same location, well, tough luck. You're never going to get it. This is what we call a conflict miss. And when you are trying to resolve the issues and try to find the solutions, this is one of these problems that you have, that you're trying to solve. So what's the easiest solution to this? You say, why does it always have to go to this one thing? Give him a couple of options. You have a large cache. Why is this like communist thought that you data, this is your space, don't move from here, you know? Let him go to someplace else. This is called set-associativity, allowing the same data to map to more than one place. Set association can be, I mean, if you say that we have, instead of having, you know, one column of 8 locations, you can have 2 columns of 4 locations. If you keep the size of your cache the same, the number of bits the same, and instead of having a cache with 32 locations where everything maps to exactly one address, one index bits, you say for every index I have 2 possibilities, but I now have only 8 locations I can choose from. It's the same thing. I'm just reorganizing how I am dealing with this cache internally. So instead of saying, this is where I store everything, you divide it into 2 and say, this is my first set, this is my second set. I have a cache with set associativity 2. Every address can map either to here or to there. Yeah, makes sense? So, this is then the solution. You say, I have now 2 ways where you can go. I can store one tag here, I can store one tag here. I have 2 solutions for this. And data, so the one that corresponds to this tag is stored here. The one that corresponds to this tag is being stored here. Now, the tag is larger. I have 3 bits because I don't have so many locations as before. I have only 4 locations, which means that I only need 2 bits, but the rest seems to be the same. So once I have an address, I'm checking the tag. So the address has something. I'm checking it against this one and this one. If either of them is a hit, then I know which one is a hit. And from this decision, I can select it was either here or here. Now I have my output. And once I have my output, I can select the byte that I want out of this thing. And ta-da! Now you can say, why do we do, what is good for this? I mean, why do we do this? Because this reduces conflict misses. Which is good. Don't worry, it will be, you can go one more step And you say, why don't we, I mean, okay, we did it one way, why don't we do it 4-way? You say, oh, okay, we can do it 4-way. It looks like this. Now my tag store has 4 possibilities. The data store has 4 possibilities, and then I select. And I say, okay, why don't I have fully associative cache? Which means that, I mean, it's the capitalism of cache if you want. Every data can go anywhere in the cache. Now you have something like this. There is 8 different tags. We have to check which one is where and then decide. And then once we have it, we have to fish it out and go there. So there is an obvious penalty you're paying. With the direct access cache, you know exactly where to look for in the cache. 2-way set associative, you have 2 options. 4-way, you have 4 options. There is logic, there is time, there is effort involved in determining where your data is. So you are trading off the conflict misses with the complexity of making sure that you can find the data. Fully associative caches are the dream of everyone, but they are extremely expensive. I mean, technically, you have to compare this address to every door in a street, like, are you this, are you this, are you this? Maybe you can parallelize it to some degree, but it is very expensive. Okay, so let's take a break. After that, we talk about some other properties of caches. Okay. Does this work? Yeah. So a couple of things I missed in the previous hour. So we were talking about different misses in the cache. The first, I talked about the conflict one. I should have also talked about the more obvious one. One of the misses in the cache is what we call capacity. And the capacity miss is actually very simple. You have a data structure which is, I don't know, 16 kilobytes that you are constantly accessing, and your cache has only 8 kilobytes. The data that you're accessing is not fitting into the cache. So this is what we call, you have a capacity miss. It looks at some point similar to a conflict miss, but the difference, the key difference between a conflict and capacity miss is the following. You could have the entire cache empty and still have conflict misses, because the way you are accessing the data always comes to the same location. But the capacity is you're simply accessing too much data. The data structure you're looking at is larger than the capacity of the cache, hence the capacity misses. The other thing that I missed while I was trying to explain it in the break was that actually what we are trying to do is determine the parameters of the cache that we are designing. So the first obvious one is probably the size of the cache. Is it 4 kilobytes, 8 kilobytes, 32 kilobytes, 1 megabyte, whatever. So it means how much data am I storing in my data storage of the cache. And this one obviously determines how much capacity misses I'm going to have. So this is associated with the size of the cache. On the other hand, you say, just make it larger, right? What's the problem with larger memories? Yeah, they get slower. So you have to also negotiate the size of the cache, the capacity misses that you have, versus how fast the cache is. Would you rather have a cache that can return data in one cycle, but is 8 kilobytes, or you have one cache which is 64 kilobytes, but returns data every 4 cycles? And the good news is you can all simulate these things, and there are a lot of simulations and analysis being made. One problem that you always will have is these analyses depend on the data access pattern that you have. How are you keeping your data? How are you accessing your data? And according to that, you will have these things. Now, the second parameter that we were discussing, we just discussed, is the set-associativity, meaning how many places how many different locations can I place the data that I'm putting into the cache? Direct cache is the good one, simple one, if you're a hardware designer. Fully set-associative caches are the dream if you are like this, everything is so nice, everything can go everywhere, but it's a nightmare if you're trying to do the hardware. So this is the second thing that you are trying to balance out. How much conflict misses are you going to tolerate versus how much complexity you have in the cache the complexity can be so much that the access time you may need multiple cycles to get to it. Sorry, yeah, I didn't see the question.
Is the question what is stored in the cache and what not open to the programmer or the compiler, or is this completely done by the microarchitecture?
That's a very good question. The question is, who decides what comes into the cache? That was actually, we were discussing it yesterday. There are two main roads you can go. Either the programmer manages everything, user-managed caches, scratchpad memories, or it's all only taken care of automatically. There are some tricks in software to how shall I say, prime the cache prior to running your loop. So the software people, if you know what's underneath, you know what's the intelligence between moving the data, before you are running your very data-intensive operation, you could do some strategic memory accesses so that your caches are primed, meaning that the data that you will be needing soon can be brought in. All these tricks are part of the trade. And you can only make use of them if you understand what is happening. I'm laughing at it because the slide counter says 14 of 81. So I don't think I'll be teaching this much more. Honor will kill me. But okay. Sorry. Okay. So now let's just trace back and talk about the higher associativity. Higher associativity is higher hit rates, slower cache access time, because you have to make more comparisons and it's more expensive. And then we have also these graphs. And these graphs are very, here there is absolutely no numbers across the graphs, but in the books you will see a number of them. It just tells you how it works. The first trick that you do brings you the most. And then as you increase associativity, it kind of flattens out. This is like the rule of diminishing returns, that the most out of these tricks you get is when you first apply them. So from direct mapped cache to two-way set associative, you get a lot of gain. From 2 to 4, you get decent gain. 4 to 8, 8 to 16, 16 to 32, but you are putting a lot of effort in making them larger, but you are not getting enough for your effort. So now there is also some interesting issue once you go to higher set associative caches. And let's be clear, in high performance computers and things you're looking at, at the important parts, level 1, level 2 caches, you very rarely have direct mapped caches. You have at least some set associativity. And now there are a couple of decisions, because you see, the data can go 2 different ways or 4 different ways. The same cache location holds multiple data. So you have these decisions to make. Where do I insert one? Which one do I keep? And which one do I get rid of once there is one more data coming into the same set? Now, this is an interesting discussion. The decisions to this are lead to different results, different caches with which you can work. So one thing that we will discuss right now is what happens when we have new data coming in, which means that one of them has to go. How do we decide which one is going? Okay? And so you can say, I have 4 locations where I can put some data, and I'm also keeping track of whether or not this data is valid or not. And if the data is not valid, then it's very easy. If there's new data coming, I pick any invalid block first, because there was nothing in it. Who cares? And it's not very easy to be really random, You say, okay, let's first pick this guy. And then, if all of them already have some valid data, what do I do now? Is one data better than the other one? All data are equal, but some data are more equal, kind of thing. This part in 1984? No. Okay, so now you go into computer architecture literature part where you can discuss this a lot. Shall I do it randomly? I mean, they were there anyway. I mean, all of them are as good as each one. Or, you know, should it be that the first one that I put should be the first one I replace? Should I find the least recently used? Maybe I have 4 data. 3 of them I've been using constantly. The other one just happened to be there, bystander. Maybe I should identify this one. But how do I do this? Or I take the one which was, you know, not most recently used. Any one but the most recently used. Or least frequently used. Like I have 4 data, I keep track of them. I use like this guy 4 times, this guy 5 times, this guy 6 times, and this guy 1 time. Let's kick this guy out. Yes, sorry. Maybe. FIFO, the least recently used. No. Nah. Not necessarily. It's a tricky one, but it may... I'll get back to you after the lecture. I'll read up and find the reason. So there are actually, I mean, if you look at what kind, I mean, just thinking about it, you will realize there is a lot of different things you can do. Now there comes the question, how does this affect the performance? And the performance you're thinking about is, how fast does my program run on average on the collection of choices I made for the memory hierarchy? How many caches do I have? What is the size of each one of them? What is the set associativity? What's the block size? What's the eviction policy? Let's also add that. And all of this as a total is going to give us some system performance numbers that we are looking at. So just the least recently used one. If you say, I want to get rid of the least recently accessed block, the problem there becomes, you have to know which one was the least recently used one. It's very easy if you have a direct map cache, because the least recently used one is the one that's there. But if you have 8, how is that? Do I have counters? Like every time I access one block, am I changing the counters of the other ones? And, you know, so the two-way set-associative cache, you will also see in your textbook, you can get away with this by using a single bit. You know, every time you access one and it's in the other one, you just can flip the bit. But if you have 4-way set-associative cache, the least recently used one to determine that one is not so easy. So maybe you say, I don't need this. I don't need to implement a true LRU or the perfect LRU. I can have some combined things. So say, why? Why is this an issue? Because before I can complete this operation, I cannot go on with my normal life. You see, if I have to bring in some data and I have to make a decision, and that decision takes a lot of time to do, needs additional bits to store, needs additional power, area, time that I have to insert, I'm not doing a good job. Maybe I can find something which is almost as good, much simpler to implement, but doesn't cost so much. So I will not go through all of them because it's also not exactly the field that I work with, but there are some examples. The not most recently used is a good one, right? You just mark the one that you recently used, and all the others are 0. So you pick one at random, and unless it was most recently used, you pick the next one. And hierarchical LRU, you have n-way set-associative cache. You divide it into 2 groups or 4 groups of smaller set-associative caches and implement a simple least recently used algorithm there. Or you know, just pick it at random. So now there is also the question, and this is always the questions that we are asking. Unfortunately, they don't have a direct answer. If they had a direct answer, you could say, this is the way to do it. you want to evaluate, is LRU better or is random eviction policy better? Why do I say this? Why don't we know which one is better? Someone else? Yeah? Testing in real-life applications. Yeah, but are they different or do they change? I understand. You have to test it. But if I test it, will I get different results? Why would you get a different result from someone over there? This is the, yeah, okay.
So the problem is that the answers depend on the input and they can vary.
Exactly. So the problem is the data access patterns, the application you're using, how you are accessing the data, and that is not something that you can set in stone in your architecture. That is user dependent. And you have to run benchmarks, you have to run a lot of different benchmarks, or maybe you don't want to run different benchmarks. Maybe you are designing an architecture which is very well designed to one set of problems. You don't want to solve all problems in the world, but find a set of choices for your architecture that fits a particular problem very well. These days, this would be, for example, machine learning. Everybody loves machine learning these days. So you will see a lot of architectures that have been tuned to accelerate machine learning programming, and you can be sure that people that are looking into designing the caches in these systems were looking at some trade-offs that favor that. There's a question?
Would it be a possibility to give this cache management logic access to the program instructions? Like, for example, search the instructions for load words and like predict what data is going to be used next.
Yes, actually there are, I mean, it ties to the same thing. The question is, can you expose the caching decisions partially to the software? Yes, there are systems where you actually manage these faster memories yourself directly. However, you have to realize some of those choices, for example, the size of the memory is not something that you can tune by software. It is either there, you have the capacity, or you don't. It's not a question, you just stretching, okay. Okay. Just coming back to the, this is not only with the LRU a problem, we have these problems called set trashing. This is when the access patterns to your memory exceeds the capabilities of the cache. So in this case, you have a 4-way cache, and you have cyclic references to A, B, C, D, E, and when you have the least recently used policy, it just doesn't work. You keep on evicting the one that you should have kept, and you end up in something. And in practice, depending on the workload, even random ones and LRU ones could be just as well. So optimal thing, if there was one, we would have known about it, but there is, once again, in the lecture, many papers written on this thing, and we are staying on this one because looking at also the author's case for MLP-aware cache replacement, so you can also see that there is research work going also into these structures. Okay, so set associativity we have talked about, just a second. And we were always talking about this tag. We said there is a wallet bit, there is a tag bit. If you are doing LRU, there must be also some other things. So let's just quickly take a look what's in a tag store entry. Remember when we were talking about the caches, this was our data store. Here we were storing the data that was in the memory. And this was the part which was telling us whether or not we had the right entries in the cache, whether or not they were valid, etc. So the tag store has at least a wallet bit. It has at least a tag. And depending on what kind of replacement policy we are using, there will be some associated bits with this replacement policy. We also have sometimes a dirty bit. It's nice, you know, It wasn't probably politically correct at the time when they were coming to this. How dare you call a cache line dirty? A dirty bit is used, we almost always think about it as reads, but you are also writing. You can specify that you actually made some changes to the cache, that the content has been changed from the time it was read from the main memory. So this means that the cache is dirty, we made some changes, and these changes have to be reflected back to the main memory. As you see, we started with very simple things. We didn't even think about wallet bits. Then we added wallet, the tag we needed. We have replacement policy bits, and we keep on adding things. So while we are talking about handling writes, when we talk about dirty bits, we have to also look at these two basic options. So mostly when I explain, I'm saying that we wanted this data, we bring it to the cache, we work on it, and everything is fine. We are assuming that I'm reading this data. You all know that when you are running a program, you are writing almost as much as you are reading, because you are processing, you are making something out of the data. And the question becomes now, what happens to the data that's in the cache that you want to write to? Now you have basically two options. The first one is write-through. In the write-through, if there is an address, it comes here, you want to write to this thing. You check if it's in the cache. If it's in the cache, you write it to the cache. You tell him that everything is okay, let's go ahead. And then you still take the time and go to the main memory and make the change in the memory location itself. Now, the other one is write back. This means that as long as the data is in the cache, you do all the reads and writes from to this location. Only when it is time to get rid of this data, you realize that, hey, I modified this data, so before I get rid of this data, let me complete the write to the memory. This is called write back. Now here's the interesting question. When do I have to write it back? Yeah?
There are two times when you have to write it back. One is accepting you evicted, and the second time is another processor.
Let's just say at one processor at the time, yeah. But the thing is, we have this eviction policy, right? We discussed a little bit about it. I skipped over it. There might be a lot of reasons that I randomly, more or less, decide that this data has to go. There's another data that wants to take its place. It's not the program. It's important for you to realize it's not always that the program says, good, I'm done with this data. Let's move it back to the memory. This is handled automatically, and at some point, the cache decides that this guy needs to go back. And then you realize that, oops, this is dirty, so I have to complete my write. And maybe you want to wait until it's actually written there before you let everything go through. So the write back is actually very good because it can combine multiple writes to the same block before we actually do this costly write. Imagine that I have this writing block. I write here something, here something, here something, here something, and I could move actually all this data at once and save a lot of effort. And this is an advantage, so you can save bandwidth. The problem is that we need to still keep somewhere in our tag additional information, bookkeeping information about this place. So write-through is much simpler, and there is another advantage. Once you are writing through, it's there's not necessarily one level of cache, right? So if you write it through here, this one writes to the next level, that one writes to the next level, that one writes to the next level, all the way to the highest level. So all levels of cache are then kept up to date, which is kind of nice. But we have to constantly move data back and forth where we could have saved a lot of things. So these are two things to keep on in mind. Now, this was when we had only one processor. In a few minutes, well, hopefully, I will come to the slides where we talk about multiple cores. There you see it is going to be more interesting. So, handling writes, there is also this thing, do we allocate a cache block on a write miss? So we want to write something here, do we bring the data here? Do we bring it here? Or, you know, if I want to write to a location, it's not in the cache, let's not bring it into the cache, let's just write it to the main memory. I didn't read from it, I just want to write it. It's not in the cache, so shall I first bring it, or shall I not bring it? Well, you know, so the allocate on write miss has its advantages. It's much simpler, but it requires that you transfer the whole cache block back. So, you know, it has to come from all the way, main memory has to fill all the caches before you can try to do this. If you do no allocate and you're writing to it once, it's a location that you just dump the data and you're not reading it back from, don't bother the caches. Keep the caches free. You know, if I have to bring something into the cache, I'm going to kick something out. And maybe the thing that I'm kicking out is more useful to me than the, you know, continuous write I'm making to some part of the memory, especially if I have write-through. So these are all questions that come out of because of the tricks that we played in trying to make sure that this processor sees a big memory as something that they can access faster. And you realize how many branches we already made. You know, with sizes, associativity, block sizes, and everything. So this is the same thing. Let me get. There are also caches where you realize, just out of the same problem, it's a solution to this. When you are trying to write it, say, hey, the block size is good for reading, but the block size is not good for writing. So let me use divisions, different sizes, sectored caches, where I have my one cache line separated into multiple subblocks. It's all the same tag, but I am keeping the dirty and wallet bits of individual subblocks, but I keep one overall tag for the entire block. Why not? Let me just... The next discussion that we have is instruction versus data caches. Shall we keep them separate, or shall we keep them unified? Also a good one, right? Imagine that for every instruction that you execute, you have to fetch an instruction somewhere from the memory. Your program counter is telling you where the next instruction is. You read it, that one tells you to go to the memory, fetch something, write, multiply, accumulate, whatever. So on one hand, you have these instructions coming continuously into the program, and then at some completely different location, presumably, you have the data being fed into this program. Shall I keep them, shall I just have one cache that handles both of them, or shall I separate them? So the good news is, if you have it unified, I don't need to a priori decide whether or not how much memory to allocate, how much of my very expensive sizes to allocate for data and cache. I can say, I have one cache, this is as big as it gets, it's a very nice one, and if I am unified it, data, program, everything resides in the same space, I have everything very nice, and it's simple. But then, the instructions and data have, they are not really correlated somehow. You know, the instructions do their own thing. They have their own loops. They have, you know, one after another. Then they loop back and do their things. Whereas data is what you are trying to process. You have a matrix that you're going through, a linked list or something like that. And the decisions you made for associativity, block size, eviction policy, etc., may conflict with each other. And you might have a lot of issues because of that. So, when you come to processor designs, the first level of cache, the cache that's closest to the processor, is almost, these days, always split. And the main reason is because the instruction and data are accessed by completely different parts of the processor, so you merge the first level cache into the fetch unit, and you merge the data cache to the load store unit or the memory write back unit that we have in these things. And for almost all processors that you have seen or are using, the first level cache is split. The higher levels are usually unified, almost always. So this is one of the cases where, of all the parameters we discuss, that 95, 98% of the cases you can show that this is the better answer. You can use many different applications, try it out, and see this is happening. Now, so you are trying to make your multiple level of decisions, and now you have all these parameters you can look through. Somebody has to sit down and decide what is the best thing to do. And if you, simple idea would be, let's exhaust all the possibilities, right? Let me say for all sizes, for all set associativity, for all block sizes, eviction policies, for all applications, let's run everything, and I'll find the golden one. Unfortunately, there are too many options to go through, so it takes a lot of time, and there is actually space for people who know and understand, have experience in it, to make better decisions than exhausting the search space. The first decision, that the decisions very, very much affected by the cycle time, is actually the primary question when you are closer to the processor. If you are executing the instructions, you need to feed them with a constant rate of instructions. If the processor is running faster than you can supply them instructions, it's no good. So that's the balance you have to keep. How fast can I make the processor versus how much instructions can I feed them? At the same time, not every instruction will consume data, but some of them will consume multiple data. How can I keep the pipelines, which are the expensive, fast things that do actually the stuff, busy? And you will end up balancing these parameters to match the cycle time, which is the pipeline within your processor. In order to reach those speeds, you will end up being small. You cannot afford to have higher associativities, and the latency is critical because it would be ideal if you could have one cycle. From one cycle to two cycles, there is like 100% change. So trying to stay small there is much more important. And the tag store and data store, if you want to do this fast, you want to make this decision, check the tag, find whether or not there is data. If there is a hit, find the data here, extract it from the cache, return it as fast as possible. You want to do this parallel. You don't want to say, okay, first cycle, let me see if there is a tag. Tag is there. Second cycle, let's get this. Third cycle, let's pick this thing out. You don't want that. You want to do it as much as you can in parallel. The secondary level caches, so it could be L2 and higher, you need to now balance the hit rate and the access latency. You usually have larger ones and higher associative things. The latency there is not so important. So difference between, let's say, 10 cycle of latency and 11 cycle of latency is not as large or is not as important at that level as it is in the first one. If you look at the recursive thing, it starts with the latency of the first cache plus the miss rate of the first cache times the access rate of the second cache, etc., etc. You will see that the higher you go, the less you care actually about the importance of the access latency goes down. What also happens is that the tag store and data are now accessed serially. It's not very easy. This is not an easy task. You have the tag, and here you have the tag location, and you have multiple of them, trying to see in an 8-way associated, do you match, do you match, do you match, do you match? And it's actually a lot of work. You may want to go through that one by one. First make this operation, then make that operation. It's okay if that decision takes a few things. Now, I have some things. Okay, so this is what actually ends up determining it. Let's see if we have everything. Cache size, the parameters. Okay, block size, set associativity, replacement policies, or insertion and placement policies at the same time. So when we talk about cache size, we are talking about the total data that we have. We usually do not include the size we have for the text or the wallet bits and dirty bits, etc., etc. We are talking about the area that we use for actually the data storage. And the bigger can exploit temporal locality better, because the data stays there. But it's not always better. So there is the hit rate starts increasing, and as we see in the other examples, the problem is the smaller caches are faster, the bigger are slower. So if you increase your cache size, after a while, this cache, I mean, you have to consider the following. This cache is not as fast as this cache. So if you have a cache that is having maybe 95% of hit rate, but is working 10 times faster than someone that has 98%, maybe it's actually better to have a smaller cache that misses more often, but works a few times faster. Too small a cache, if you come here, actually doesn't work at all. If you are working with larger blocks and it doesn't fit, you are continuously having capacity misses, it's also not helping you. It's difficult to find a balance, and what you want to do is you want to be able to partition your data so that fits into the lower level of caches for a given amount of time, that you can take it there, operate on it really fast. When you are done with it, it automatically will go out and you move to the next one. Now, the block size was for the spatial locality, and we were picking the block sizes. So block size of 1 means you are just picking 1 byte or 1 word. Block size of, I don't know, the exact size of the cache means that you are just completely replacing the cache with a, 1 block of data. And you will also see in the book there are also some numerical examples taken from real simulations. You will see that it starts increasing, and then after a while it starts decreasing, because spatial locality is not the only thing that you have going on in the cache. It might be very good for some amount of operations, but not everything you do has spatial locality. The problem also is, if you are replacing larger amounts of blocks, you run into a second problem that we didn't talk so much. There is the bandwidth. If you need to replace 4 kilobytes of data in this cache, that 4 kilobytes of data still needs to be transferred within a reasonable amount of time from this memory into this cache. It will take longer. Okay. So let me just come to the other one. Associativity, we already discussed about this a little bit. I'm not going to repeat it very long. Large associativity is good. It reduces the conflicts, but it's much more difficult to implement. Smaller associativity, or in the limit direct mapped caches, are simpler to implement. They work very fast, but you end up having some issues. Now there's a good exam question. Is power of 2 associativity required? No? Save it for the exam. No, you're going to ask me, right?
I don't think it's really required here. Unlike the amount of sets and such, because there isn't really, it's not really linked to the address.
Yes. But you can also make some other argument saying that powers of 2 are much easier to multiplex and do this thing. But it is not, for example, you would have to have the number of rows have to be a multiple of 2, the cache lines. The block size has to be a power of 2, because you are mapping directly the address bits to that. But the associativity technically is not one of them. So classification of cache misses. And do you remember the Mealy-Moore? Did you see Mealy-Moore finite state machines? Wasn't it annoying that you had like these 2 finite state machines? They are both called, start with M, and you have to memorize them for the exam. Now it gets better. There is a third type of miss that I didn't talk about. Those are compulsory misses. Basically, this means that you just started programming, you just started running your program, the cache is empty, there's nothing in it, so every access to the cache is going to miss. Not because the cache is designed in a wrong way or something like that, because, you know, you are just starting, there's nothing in the cache, so it's going to be a compulsory miss. So this is the one that we didn't talk. So this is the first reference to an address always results in a miss, unless, of course, if we can use the spatial locality and somehow a previous access brings in magically a few of the friends in there and we are accessing it. The capacity miss, we talked, is cache is too small to hold everything. And the conflict miss is, this is a critical one. Any miss that is neither a compulsory nor a capacity miss, it's a correct definition. It looks very much like a capacity miss for some of the people. Just notice that, go to the extreme, think about a direct mapped cache. You could have all the cache empty, and you could be continuously having conflict misses on the same location. The entire cache is there for you to use, but you cannot use it. So this is a case where you do not have any problems with the capacity. The cache would have the space. You are just having a very bad policy for placing the data you want into the cache. So how can you reduce each one of them? Well, the compulsory misses are actually kind of fun. The policies, the caching, is not really helping. It's the first time for everything. And I mean, unless there is some miracle happening in the background, the data magically cannot appear in the cache without us knowing anything. The thing that helps, there are techniques called prefetching that you, at the part of a program where you are still not, let's say, in the loop, you can already make some accesses which will use either spatial locality or something like that to bring the data you are about to process more rigorously into the caches. And there are some systems like the GPUs I was talking about where you can manage the memories yourself. So for conflict, more associativity works. There are some other ways that you can make it work. One of them, I mean, you can have more randomized indexing, or try to, if you know what the cache sizes and the associativity is, and if you have a data structure that is always hitting on that, you could have some better indexing or give some hints to the compiler to help you out with this. Capacity, well, you can use a bigger cache. It will be slower. You have to look for ways of doing things, having better decisions here, for example, in your eviction policy or in the set-associativity. Now, how to improve cache performance? I have 3 minutes to finish it. I hope I can manage it. The most important thing is you want to reduce the miss rate. Once you have reached your minimum miss rate, then you want to reduce the cost of the miss latency, or the cost that you pay for missing in this level of cache. And then you can try to reduce the hit latency or the hit cost. This sounds like fishy. This just means that you want to, in the end, just reducing the miss rate doesn't help so much if a cache hit requires 1,000 cycles, for example, in your first level cache. It's just like a main memory, It will never miss, but it is also ridiculously slow. Okay, so the thing is, it's not these 3 independently that you have to optimize. You have to optimize all of them together. Now let me just have this thing about restructuring data access patterns, just to see this in an example before I let you go. So we are processing now some data, and we have the way that we have the data layout or the data access can have a huge impact on how fast our program is running. Now, we have a column major operation, so xi plus 1 follows xi in memory, and xij plus 1 is far away from xij. So the data is organized in this way and not in this way in the memory. Now, if we are accessing our loops for rows and for columns, and then we are operating on consecutive things and we are summing them up, this is one way of accessing it. And it will result in very poor code because the data in the columns, we are going over the columns and they are not next to each other in the memory. But if we flip them now and we go 4 columns and 4 rows, now every access here, I mean the first access is most probably going to bring, due to the spatial locality, the next blocks also into the cache, and the next few accesses will have actually the locality so we can work with it much easier. So this trick is called loop interchange. The other ones can also be done in which you, for example, manage your the sizes of your of the code into divide your loops into computation chunks so that each chunk that you iterate upon has exactly the size of the cache of the lower level caches that you are interested in. This makes an enormous amount of difference in the speed of the code that you are running, and understanding this a little bit more will also help you in the code. Thank you very much. This is all from me this year, so I hope the best in the rest of your classes and exams. I'm innocent in the exam preparation, so Onur said, no, Frank, stay away from asking questions. I wish you all the best. Thank you.